All right, so now we need to talk about what's happening in the loops of Henle. So we just left the proximal convoluted tubule, and the about 70% of the stuff's been reabsorbed here. Okay, but we still got 30% left going. So the filtrate heads into the loops of Henle this way. Okay. So a couple of things happen here. So in the descending loop of Henle, the descending loop of Henle is permeable to water, but not to solutes. So it's only permeable to water. And that's in the descending loop of Henle. The ascending loop of Henle the ascending loop of Henle is not permeable to water. So it's impermeable to water, and it actively pumps out solutes like sodium. Okay. Weird. So descending tubule is permeable to water, but is not permeable to solutes. And the ascending has little pumps on it that pumps out solutes like sodium. That's weird, okay? Well, remember, 30% of what needs to be reabsorbed, or what was out, still needs to be reabsorbed, or some of it does anyway. So now that we've gotten through that 70%, now we end up in the loops of Henle and then the distal the distal convoluted tubule, where we're fine-tuning things here. So how do things move between the tubules and this interstitial space here? Because up here in the proximal convoluted tubule, we had transporters that did it, okay? But we don't have that here, all right? Well, this, I have here, you can see that this top up here is the cortex and the medulla is here. And again, reiterating that the medulla is where the loops of Henle are. And the medulla is a very weirdly salty environment. The concentration of the solution within the medulla is different than what it is in the cortex. So the concentration, we call it osmolarity. And that's the concentration. That didn't work out too well there. So it's the concentration of a solution and it's stated in milliosmoles per liter. Okay, so it's basically the stuff in the fluid. Okay, so in the cortex, the the osmolarity is the same within the tubes and the blood and the interstitial space. We call that isoosmotic. Iso meaning same. So the osmolarity is about 300 milliosmoles. So that's 300 in the interstitial fluid. It's 300 in the tubules right up here. It's 300 in the glomerulus and the arterioles, all of that. So 300 isoosmotic. But as you go down into the medulla, the osmolarity changes. The osmolarity in the medulla gets progressively higher as you go down. The medulla gets saltier and saltier as we get lower and lower into the medulla. So again, the osmolarity changes, all right? So as we come down into the loops of Henle, so into the descending loop of Henle, the osmolarity of the area around it is going to be higher. Okay, so it's going to change the osmolarity of the fluid that's coming down here. Okay, so if the osmolarity is 300 and it's going into an area where it's higher than that, so 500, then what's going to happen? Okay, so that means that this area around this tubule, as this 300 osmolarity milliosmol filtrates coming in, so there's a lot more stuff, salt, in the interstitial space than there is in the filtrate. So that's going to mean that the water is going to want to leave, go towards the solute. And it's going to want to leave until it's equal. Okay? So as it goes down, let's make it 400, 500, 600, 700, 800, 900. It goes down to about 1200 here, milliosmoles. So it continues to get saltier and saltier as it goes down here, which moves the water out. All right. The medulla area doesn't get, the osmolarity doesn't change because in the ascending loop, we're pumping out solutes into the interstitial space. So that's keeping it really salty. Okay? It's keeping it salty and keeping water moving out of the descending loop. So by the time the filtrate gets to the bottom, so by the time it gets here, it's really, really concentrated. The water's gone, and so the filtrate there is really concentrated. So as it moves up in this direction, now we're pumping the solutes that are here out of it, so now it's getting less concentrated. So that once it gets to the proximal convoluted tubule, the osmolarity could be as low as 100. Okay? So this is how the solutes are reabsorbed and sort of moved around once it gets out of that proximal convoluted tubule, because out of the proximal convoluted tubule, there are no more transporters to do it. So we've got, all we have are these little pumps that are pumping out solutes, and then this other side is dealing with the water. All right, so once you get to the proximal convoluted tubule and the collecting duct, so here's the collecting duct over here, basically the PCT and the collecting duct, these tubes are affected by hormones. And these hormones sort of maintain and sort of um, finish the urine formation, okay, based on what's going on. Because as I said, we did have, these cells here, the macula densa cells, that are monitoring this filtrate as it goes into the proximal convoluted tubule. So the proximal convoluted tubule and the collecting duct are going to be affected by hormones such as ADH and aldosterone. And that will complete the concentration of the urine that's going to be excreted. So based on, blood pressure and blood volume and things like that, that's going to cause the secretion of these hormones, and they're going to target the kidney, and this is where they target to basically say retain water, get rid of water, whatever. Okay. So this area here, this weird, salty, crazy change in osmolarity down the medulla, that's called the countercurrent multiplier. And that changes the osmolarity of the filtrate as it comes down the descending limb and as it goes up the ascending limb. Okay, so the osmolarity of the filtrate is being changed based on this weird osmolarity change as it goes down into the medulla. Okay, so the next video that I'm going to show is we're going to put the bloodstream in with this, but I want you to watch the video after this, which is not my video, which is a video that actually shows this countercurrent multiplier in action, and it'll help you understand that a little bit better.